Hello, and welcome to this presentation on the fundamentals of drainage design. Throughout this presentation, we will delve into the essential aspects of drainage, including the rationale behind its necessity, the regulatory standards and guidelines that shape drainage design, and the fundamental terminology commonly employed within this discipline. So, why do we need drainage systems? The primary rationale is to take runoff from the catchment when it rains and convey it to a particular location like a watercourse or existing drainage infrastructure. These systems tend to be called stormwater sewers. Stormwater drainage takes up a large proportion of today's work within the industry. Alternatively, sewage, which is wastewater from households and industrial infrastructure, needs to be transported to a place in which it can be treated. These systems are named foul or sanitary systems. Modern-day drainage should be separated. However, older systems built in the Victorian era are often combined, where both foul and stormwater goes into the same pipes. This causes problems during heavy rainfall because the systems become overloaded with stormwater and the resulting mixture spills to the river or sea via combined sewer overflows or CSOs. Reducing the number of CSOs and the volume and frequency with which they spill should be a priority for water companies. On top of that, the need for drainage can be attributed to influential drivers such as the climate emergency and rapid urbanisation. The pressures that these drivers provide strain the current systems, which is the reason why traditional drainage systems are becoming less favoured. Within the UK water industry, there are a number of stakeholders which influence policy, standards, research and guidance. A stakeholder is an individual, group or organisation that has an interest or concern in a particular subject, so in our case, drainage. Key stakeholders will inevitably include both government or local government. The government will often set up policy and allocate funding and investment into key infrastructure. At a local government level, you will have lead local flood authorities and SuDS approval bodies who provide standards and guidelines as well as scrutinise planning applications which include drainage strategies. Another stakeholder will be agencies such as the Environment Agency or the Scottish Environment Protection Agency. These agencies are responsible for environmental standards by making sure companies who interact with the environment work within regulated limits. They also look after all of the major rivers found within the UK. Regulators such as Ofwat or Wicks define how much all 10 private water companies in the UK are allowed to charge and should ensure that customers get value for money by setting price controls, conducting regular reviews, and holding water providers accountable for delivering high-quality services at reasonable costs, whilst also promoting fair competition within the industry to drive innovation and efficiency. A proportionally large stakeholder found within this industry will be the developers and civil engineering consultancies. These particular companies will be responsible for the design and conception of drainage systems found within the UK, addressing various urban challenges such as reducing environmental impact, enhancing energy efficiency, and implementing innovative technologies. Professional bodies and research institutions in the water industry serve as knowledge hubs, advocates, educators, and innovators, helping to ensure the responsible and sustainable management of water resources while supporting the professional development of those working in the sector. Their roles are essential in addressing the complex challenges related to water supply, quality, and environmental stewardship. All in all, the collaboration between all of these stakeholders exemplifies the interdisciplinary approach found within the water industry. In this industry, there exist several key policies, standards, and guidelines that are important to understand. To begin, we have the design and construction guidance for both foul and surface water sewers. Historically referred to as sewers for adoption, these standards guide the design of new systems for eventual adoption by local authorities or water and sewage companies, hence the name sewers for adoption. In any case, this document offers comprehensive, in-depth guidance concerning the design of structures such as pipes and manholes. Secondly, we have the Syria C753, or better known as the SuDS Manual. This is a widely recognised document produced by Syria in 2015. This document provides thorough guidance on sustainable drainage systems, all the way from philosophy and approach to technical detail and maintenance. In the design of sustainable drainage, this document is a must-have. Additionally, we should acknowledge various other example policies, including the statutory standards for sustainable drainage in Wales, the non-statutory technical standards, and the National Policy Planning Framework. These documents establish regulatory guidelines for the construction and development of projects related to drainage. Whilst they may be somewhat less central to drainage design, they retain relevance within the broader industry. This slide features an illustrative cross-section of a typical road. It is important to note that this representation is not an exact depiction of every road in the UK, but rather a general conceptualization of the common drainage infrastructure beneath our roads and pavements. You've likely encountered these familiar grated metal structures along road edges. These are known as gullies. Gullies play a crucial role in gathering surface runoff and directing it below the road surface, often connecting to stormwater systems, for instance. In addition to this, you may have seen these circular or rectangular metal covers on either pavements or in the middle of roads. These are manholes, and underneath these manhole covers will be a circular or rectangular chamber connected to a pipe network. These chambers, linked to extensive pipe networks, serve as access points for maintenance and inspection, enabling utility workers to monitor and maintain the intricate system of pipes that transport wastewater. And finally, we have to consider the fact that underneath our roads and pavements, there will be other structures that provide gas, internet, and drinking water, for example. These utilities are just as important as drainage systems and are also integral to the functioning of urban areas. Gas pipelines, internet cables, and water supply systems are the lifeline of urban areas, ensuring that residents have access to vital services. As a drainage engineer, it is common to take existing utilities into account when planning the location of potential pipes and manholes. When it comes to the design of drainage systems, it is likely that you will come across many terms in your career, some more frequently than others. In this slide, you can see a number of terms which are frequently used in drainage design. Let's start with soffit. By definition, the soffit is the highest point of the internal surface of a pipe or conduit. The lowest point, therefore, is the invert, which is the lowest point of the internal surface of a pipe or conduit. Both soffit and invert will be depicted in meters above ordnance datum. When you hear the term cover level, think of this as the surface level elevation of a structure. For example, if you see a manhole cover in reality, the point in elevation that this manhole cover sits will be the cover level. Surfaces like car parks or roads could also be the cover level relative to the drainage structure. Cover depth is the distance between the cover level and the soffit of a structure, so in this example, the pipe. Cover depth is important because it dictates how deep a pipe is laid. In an urbanised setting, we would look to ideally lay pipes at a depth of 1.2 metres. This is to ensure that pipes remain safe from the forces above, like the downward force of vehicle weight. A backdrop is a vertical drop from one pipe to another, usually with a manhole separating the two pipes. The upstream pipe will tap in at a higher level to the manhole, with the downstream pipe laid much lower. This gives us a vertical drop, or in this case, a backdrop. Backdrops can be a good method to reduce the excavation volume. It is also worth noting that throughout your career in drainage design, measurements are never in centimetres. Never mention centimetres again in your professional career. Up to 1 metre, you can use millimetres, so a pipe will be 375 millimetres in diameter, not 37.5 centimetres. Above 1 metre, you can either use millimetres or metres, so 1,200 millimeters or 1.2 millimeters diameter. As we venture into the 21st century, drainage techniques are becoming much more sustainable through both policy and necessity. Throughout your career, you will certainly come across the term SuDS, which is the acronym for Sustainable Drainage Systems. In other countries around the world, SuDS are given different names, like Low Impact Development, Best Management Water Practices, or Water Sensitive Urban Design. In any case, they will share a common goal, and that is to mimic natural drainage patterns found within the water cycle. The idea with SuDS is to use water as a resource rather than getting rid of it as soon as possible. This is why we have something called the SuDS pillars, where drainage design should look to enhance its locality through water quality, water quantity, amenity, and biodiversity. Rather than just removing water further downstream, by applying the SuDS pillars to our designs, we can make drainage have a larger impact in a positive way. Sustainable drainage structures tend to differ in shape and size, but more or less have a similar objective in attenuating stormwater runoff by mimicking natural drainage patterns. The names of these structures can also vary too. For example, a bioretention could also be called a rain garden or a tree pit. So take a moment to explore these examples in combination with real images to get a feel for how these structures are formed in reality. This diagram depicts at its most basic a traditional drainage system. For a long time, traditional systems have played a crucial role in managing stormwater and preventing flooding in both urban and rural areas. At the heart of a traditional drainage system are the pipes. Pipes serve as conduits for stormwater to flow from one location to another, usually upstream to downstream. These pipes will typically be connected together by manholes, which are access points along the system, allowing maintenance personnel to inspect the system, and are usually equipped with covers and ladders for safe entry. In many traditional systems, detention ponds or tanks are used to temporarily store excess stormwater during heavy rainfall events. This helps attenuate the peak flow of water into the system, preventing flooding around the system. And then finally, at the end of the drainage system, you'll find outfalls which discharge stormwater into natural bodies such as rivers, lakes, or the sea, or existing systems. Outfalls are designed to allow control over the rate of discharge into whatever water body it connects to. In the UK, the majority of new developments will have a limit placed on the outfall's discharge. There are several standard theories on how this discharge limit is defined. For example, the ICP SuDS method, which is based around the concept of no detriment, means that once the site is developed, the discharge rate should not exceed the current rate from the undeveloped greenfield site. Discharge rates will usually be stipulated by whoever accepts the site's discharge. In more recent times, the way in which drainage systems are designed is by strategically placing SuDS in the system from start to finish. This encompasses source control, site control, and regional control. SuDS should look to follow a drainage hierarchy to match natural drainage routes, infiltration rates, and discharge rates as far as possible. The initial approach should involve utilising rainwater at its origin. If this proves unfeasible, the next consideration should be infiltration, succeeded by solely discharging into a surface water body, then discharging into a surface water sewer, with the least favourable option being discharging into a combined sewer. At this point, we have spoken about how drainage systems are formed and what physical structures may be included. Let's now talk about how we actually design them. In other words, what information do we need to ensure that our designs will conform with reality? Design rainstorms are a cornerstone of drainage design, and without them we would lack the information required to build our systems. These storms provide crucial data including intensity or depth, duration and frequency information. Design storms offer insights into the types of storms that drainage systems must manage. This data helps in sizing and designing drainage infrastructure to manage peak flows effectively, Knowing the duration of intense rainfall is vital for determining how long drainage systems must remain operational to prevent flooding and damage. Design storms also provide information on the frequency of extreme weather events. For example, a 30-year return period storm does not occur once every 30 years, it is instead a probability chance. Additionally, it is also just as important to consider climate change in our storms. Climate change adjustments are predictions of anticipated change for peak rainfall intensity. To increase resilience to flooding, you should make allowances for climate change in your drainage systems by adding a percentage value to the return period. For example, in Bristol, for the 100-year storm event, a climate change value of 40% is required. Now we understand what design storms are. How do they influence our designs? One useful way of grasping the impact of a storm is by looking at the storm's rainfall profile. This will be rainfall depth or intensity over time displayed as a graph. To add to this, you can have a wide range of storms all the way from 15 minutes to 24 hours. The duration of a storm can have varying effects on a given system, which can be shown in these rainfall profiles. To illustrate this, I will now compare a brief 60-minute storm with a lengthier 120-minute storm. For shorter storms, in red, the profile tends to be described as peaky, which implies that the storm is very intense over a short period of time. The influx of rain is sudden and can quickly inundate the system. Shorter storms are usually critical storms for pipes and manholes. On the other hand, longer storms, in blue, have a different impact on drainage systems. The profile is less peaky and instead, the intensity is much lower. But the difference here is that the volume of rain is far greater over a longer period of time. This presents a whole different set of effects on a system, which tend to be the critical events for structures like ponds or swales. The important point is that these storms can occur at any point. The storms in this example are both for a 30-year return period. Therefore, we need to design our systems so they cope with all these storms, big and small. Referring back to the key standards and guidance slide, the Design and Construction Guidance document contains a range of standards by which engineers should follow when designing drainage. In particular, there is a two-stage process, if you will, engineers can follow which relate to the design of pipes. The first stage is to design the pipes such that they do not surcharge for a particular return period event. In this case, and dependent on site conditions, this can be either a 1, 2, or 5-year return period. Surcharging is when the water level surpasses the pipe soffit. The idea being that for these return period storms, which are very common, the system should be able to handle these events without surcharging or flooding. By using InfoDrainage, we can design these pipes for such events and check the results to confirm if we have satisfied the criteria. A status of OK indicates to us that we have achieved this. Once the no surcharge criteria has been met, we can then move on to the next criteria. This is a check to ensure that pipes will not flood during a higher return period storm, in this case a 30-year return period. This relies less on the actual design of the pipes, but instead relies on running simulations to analyse the impact of a wide range of storms on the system. What is important to remember here is that surcharging is allowed for as long as there is no flooding. If flooding does occur, there are some options to alleviate that, such as upsizing the diameter of certain pipes, or the inclusion of storage structures to attenuate peak flow. Ultimately, the overarching principle of this stage is that flooding shouldn't be present for this design return period, which is 30 years. As we have just discussed, there are standards for the design of stormwater pipes. This is consistent for the design of foul or sanitary pipes. Again, found within the Design and Construction Guidance, the document stipulates a set of rules under which foul pipes are designed. Designing foul systems is fairly straightforward because we have a good understanding of how much flow, around 140 litres, a person discharges each day. Therefore, If we know roughly the number of people who are going to live in the new development, we can design the foul system. However, foul pipes can sometimes block up, so we have to make sure that they are laid steep enough so the sewage flows achieve a self-cleansing velocity, which means any lumps are washed away. There must be a driving force that can convey it down a pipe. Therefore, foul or sanitary pipes require a self-cleansing velocity of 0.75 meters per second at 1/3 design flow. Without this self-cleansing velocity, we would have a build-up of sewage within these pipes, which would cause blockages and residual damage. This self-cleansing velocity allows for sewage to travel down a pipe without coming to a standstill. Now we have a basic understanding of drainage design fundamentals. What does an example project look like from start to finish? How do we take all of what we learned and apply it to an actual project? The first step will be to collect data on the site's topography, any existing utilities, as well as the site layout. So in this example, we can see an architect's CAD drawing of what looks like a site master plan for a housing development. We would then get the topography and superimpose this over the site to start to formulate ideas about our strategy. Then, using our skill and judgment, we start to design a potential layout of these pipes and manholes, as well as identifying the catchment areas and allocating them to manholes they will drain to. Accurate delineation of catchments is crucial as it directly impacts the volume of runoff originating from these areas. For instance, factors like the time of entry introduce a delayed effect, creating a lag between rainfall on the surface and its entry into the manhole. Furthermore, specifying the proportion of impermeable surfaces within the catchment area also play a role in determining the amount of runoff generated, all of which contribute to the peak flow. With all this information defined, it could be at this stage we design the pipes to meet the no surcharge criteria. At this point, we may look at potential structure locations to then input these storage features along with any flow control devices on top of defined outfall conditions. This is where designers may audition various iterations of their design with contrasting drainage strategies. Then finally, after the majority of the system has been put in place, we then test everything by applying a wide range of storms and return periods to see how it fares against the most critical of storms. For example, in Scotland, it is required to test drainage networks for 200-year return period storm events. By simulating these storm events, we can make further changes to the network and fine-tune the system until it is described as optimized. Once optimized, the result outputs can be generated into a report to submit as part of a drainage application. Thank you for listening to this presentation on the fundamentals of drainage design. I hope you now understand how drainage systems are built and what involves good design philosophy.